Hello everyone, this is Asarag, and let's get started with JAX Scaling Book, Chapter 3. In this chapter, we'll be discussing about sharded matrices and how to multiply them. In the last lecture, we discussed about TPUs. We went in depth about TPU architecture, how the memory is laid out in TPUs. In this lecture, we'll be seeing how matrices are sharded across the um, TPU cluster, and to do multiplications, what are different kind of cases, and what kind of communications we need to do to do sharded matrix multiplications. So here you can see that you on the left you have matrix of shape I comma j, and on the right you have 4 TPU units, and you need to shard your matrix across these 4 TPU units. Let's get some naming conventions right. The mesh is the number of devices in the x and y axis. So this is your x and this is your y axis. So this is saying there are 2 devices on x axis and 2 devices on the y axis. And for sharding, we are sharding our data I comma j along the axes x and y. We'll be understanding these subscript notations in detail later, but for now we are sharding a matrix into 4 pieces here. So let's go through the first pop quiz in the book. Consider an array of floating point 32, 120, 1024, 4096 sharded across. The I axis is sharded and the mesh is of size 8, 2. How much data is held by each device? How much time it would take to load this array from HPM on H100? So to solve this question, we have a floating point matrix, and here the first dimension I is sharded across x and y. So you have a mesh axis of 8, 2. You can see here there are 8 devices on the x-axis and 2 devices on the y-axis, and as per the notations, the I dimension is which is 1024 is sharded across these 16 devices. So hence you shard it across 16 devices, and you have 64, 4096 is shape of each shape of the matrix in each device. And in floating point 32 there are 32 bits or 4 bytes. 1 byte is equal to 8 bits, hence there are 4 bytes. So the total you have 1 megabytes of shape, and as per the question you have to load this 1 megabyte, and all of these are loaded independently from HBM. So it would be 1 megabyte divided by the bandwidth per chip. So it will take around 294 nanoseconds to load data from bandwidth to all these shards. Let's go through sharding visualization and try to understand what does this IXY means, or here what does IXJY actually mean. So for this we'll be using Streamlit to do visualization. So here you can see I have 4 devices. My mesh is of size 2, 2, and I have 4 devices, and I have a matrix of shape 4, 4, and currently it is replicated across these 4 devices. So here this x and y axis are your device mesh. So this is around x dimension and this is around y dimension, and we have 2 GPUs, hence this is in x axis there are two shards, and if you go in the y direction there are 2 shards too. And this notation is for I and J. So I is this vertical ac- across the rows, I, and J is across the columns. This is J. So you have logical data access, I comma J, and you have physical device mesh, X comma Y. So your idea is to map the logical data uh, into your physical device mesh. Let's first see how things, how matrices are sharded. So here on the left panel, you can click, let's say, X. So it says that you want to shard the I logical axis, which is this one, this direction, in the X device mesh. So if I select here X, so you can see that you have, so this is along the Y, um, um, this is a, this is the I logical mesh, and you have now sharded it across the X device mesh as per this notation here, because I have only selected X. So you can see, so the full matrix was this. Now it is sharded across these two devices. Similarly here, it was the full matrix, the full replicated matrix was here. Now it is sharded along the X device mesh. And now let's try to shard the J along the X device mesh. So J is your logical axis, this one, which is across the columns. And if you divide it, so it means you are dividing along the X axis device mesh. So if I divide it on the X axis, so you can see if you another way to think about it is, if you go along the X device mesh, this is your X device mesh, if you go along the X device mesh, then your matrix would be sharded. But if you go along your Y device mesh, the matrices are just replicated, they are not sharded. Similarly, you can delete this and select. Now what I'm going to do is I'm going to select J and shard it along. I'll select J and I'll shard it along the Y axis. So along the Y axis it will be sharded, and along the X axis it will be replicated. So I'll select Y. So you can see here, if you go along the X device mesh, these matrices are replicated, but if you go along the Y device mesh, these matrices are sharded. One thing I forgot to do was in the I logical axis, which is along the rows, if we divide it along the Y device mesh, so it is going to shard along the Y device mesh, and it is going to replicate along the X device mesh. So if I do this, I get this. So you can see here, it is replicated along the X device mesh, it is replicated, but along the Y it is sharded. And so let's try to get, so these were the individual IX, IY, and JX and JY. Let's try to get some combination of it. Let's first shard I along the X device mesh. So your I is your along the rows, and you are going to shard it across the X device mesh. So it will be replicated along Y device mesh, but it will be sharded along the X device mesh. So this one, as you can see here, it is sharded. So this is the top part and this is the bottom part, sharded along the X axis, X device mesh, but it is replicated along the Y. Now if I go ahead and shard it even further, the I logical data along the rows, which is along the rows, across the Y device mesh. So let's see what happened. So you can see here, now it is also sharded along the Y device mesh. And you can so if I just go back one step, so you can see here, so the idea is you take this matrix and we are going to shard it along the y device mesh. And now the matrix is not or the vectors are not replicated, the sub vectors or sub matrices are not replicated in any of those device meshes. They are fully they are sharded. uh, so if I click here y, you can see here now we have broken down the along the j axis, sorry, along the y axis. Now it is sharded in the y device mesh. So to get to that data, you have to traverse like this and like this and like this. So let's go through another exercise to nail this down. So suppose you have axis of sharding along J, which is this along the columns, and now you want to shard on the X device mesh. So let's shard it along. So J here along this is going to be sharded along the X dimension, X device mesh. So it will be replicated along Y and it will be sharded along X. So you can see along the Y, these two are same, but along the X device mesh, these two are different. Now we'll go one step further. So we have this. So we have J along this. So along this, we are going to shard in the Y device mesh. So Y device mesh is this direction. So let's shard it along the Y. So now you see, so you had, okay, let me go one step back. You had this, and now you are going to shard this along the Y device mesh, which is like this. So if you do this, you are in Y device mesh. So we went through IX, IY. Okay, let's do combinations of those two. So suppose you want to shard I along X. So it is replicated along Y device mesh, but it is sharded along X. Now for J, you as you can see here, the X is not present in the drop down because that would be an invalid sharding. That would be because like it will be sharding it twice along the device mesh, and that is an invalid sharding order. So so now to shard J along the Y device mesh, so this is your J logical axis and you are going to shard it along the Y device mesh. So you can see here, so you had J along this and you sharded it along the Y device mesh. So if I click it once here, you had this and you are going to shard it on this. You're going to take a knife and just like cut through here because you are dealing with the Y device mesh. So if you do it, you are going to cut through here. So you have this here, this and this and this. So that would be your IXJY. So let's try to do the reverse and also visualize that. Suppose you have I is along this and you are going to shard it along the Y dimension and it is going to get repeated along the X dimension, X device mesh. So you can see here it is repeated along the X and it is sharded along the Y. Y is this, X is this. Now here you can see, yeah, you cannot do invalid sharding by sharding two axes in the same device mesh. That is invalid. So only for J, X is valid. So so now what we have to do is along the J axis we are going to shard, take a knife and shard here. So we are going to take a knife. So just a second. So you have this and you are going to shard this along the X device mesh. So you're going to take this and shard it along X. You can see here it's present here, 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 here. So these are all different kind of sharding are possible, and please feel free to play around with this to understand what are the logical data axes, what are the physical device mesh, and how you can cut through and shard the matrices, and what different kind of configuration means. Now we'll get back to our presentation. So the chapter is on doing matrix multiplication. So one of the concepts in matrix multiplication is block matrix multiplication. So here you can see, here you had a matrix and you broke it down into smaller matrices, and we saw how these are configured. So now you can you can take a matrix and break it down across the TPUs, and you get these sub matrices, and you can have a subscript for all these sub matrices, and then you can similarly for the B matrix, which would have the same number of columns as this, would be here, and then you can take the sub matrices, and then you can do for each sub matrices which are present in a device, you can do like local matrix multiplication, and then we can have different kind of communication patterns to gather the results, which we are going to see in the further lecture. Before jumping into matrix multiplication and block matrix multiplication and how it is sharded across TPUs, let's first get some basic idea on different communication patterns. So the first communication pattern we are going to discuss is gather. Suppose you have data across different GPUs or TPUs. So these are different devices, and you want to collect all the data in one device. So this communication pattern is called as gather. Here you specify all the sources, that is all the devices that are present in your mesh, and you specify our destination. Here the destination is node 1, and all of them send their data to this node. An extension of gather is called as all gather, where you have data sharded in all devices, and instead of specifying a destination to be one node, you have destination to be all the devices in your mesh. So all this data is collected across all the devices in a mesh. Similarly, the third pattern is scatter. In scatter, you have data in one device, and you are going to send the data across for all the devices. So A goes here, B goes here, C goes here. And reduce scatter is a modification of scatter where you do some operations before scattering to different devices. So suppose you have data in all of this, and you do some operations, you collect them in a buffer and do some operation, and then send the partial data that belonged to each of these nodes. Suppose like these were 3 vectors, and you take them, you maybe take a column-wise mean, or you can take column-wise addition, column-wise multiplication, or column-wise max. And remember, like all these operations have to be commutative, so you cannot take subtraction, because in this is generally done in async, and you don't know what vectors are going to be arranged in what order. So they have to be commutative, so that even if the order messes up, you still get the same results. So this operation needs to be commutative, and you get all this result, you do some operations, and then you send the respective chunks into different devices. So let's Calculate the communication cost in all gather and reduce scatter, which have similar communication cost. Uh, for let's say you have a vector v, and you have um, x number of devices. Here for example you have 4 devices, so x is 4 and you have a vector v. So v would be so yeah, x is 4 shards and your vector v is for, you have a dimension of bd, so b and d, and it's b of 16, so you have 16 bits or 2 bytes, so you have total v size of 2 bd. So all gather means that everyone sends their part of the data to everyone else. So this shard will send data to here, and will also send data to here, and this shard will send data to here and also send data from here to here. So everyone is communicating uh, communicating and like sending over data and also receiving data, hence the communication is 2v by x, so it's like bidirectional. So as it is bidirectional, so we have a 2v by x communication, and we have and the next question is, how many hops do you need so that everyone has synced up their data. Suppose let's consider only one. Let's follow one data across the shards. Suppose you have v by x here. You send data here, and then it sends this v by x that it got from here to here, and then and yeah, that much. So now everyone has v by x. Sorry, like let me go through this again. Suppose you have v by x here. So what it does, it sends data this side and it also sends data this side. So now this shard and this shard have the data from here. Now in the next cycle, this one or this one will send the data that they got from here to this third shard. So you can see for 4 devices in 2 hops, you are able to sync the data across the cluster, and so the total time taken will be 2v by x into the number of hops, and this would be sorry, this is yeah, sorry, there were some issues with the slides, and on our explanation, like 2v by x, it's the number of data being shared in the bidirectional setting. X by 2 is the number of hops, and also to take the total number of time taken, we need to divide by the bandwidth or the data transfer speed between these two devices, including this wraparound. Generally, this wraparound is the bottleneck, so we generally take the wraparound time bandwidth to be the limiting factor, and to get a worst case scenario, we just take that. And so now you can see that the x and x here will cancel. It's a very strange result that in all gather, the time, and also in reduce scatter, which have similar communication patterns, um, here the number of shards doesn't matter. You can see here that it cancels out. It's only the shape of the array and the bandwidth. So it's a very important result that in all gather the number of shards doesn't matter, and it only depends on the size of an array and the bandwidth. Now in my previous video, I left out a question in chapter 2, which was on TPUs, and I decided to do that question after we discuss all gather mainly the communication pattern and how. So this is V by W. So after learning this, we will be able to solve these questions better. So the question was, imagine you have a big matrix sharded evenly across a TPU V540 4,4 slice, but offloaded to host DRAM on each chip. Let's say you want to copy the entire array to TPU 0, which is kind of gather. You're doing a gather operation, and multiply it by a vector VF16. How long will this take? So this is a typical TPU diagram. So you can see you have a host which is responsible to execute kernels on the TPUs. So this is similar to how you have a host and a device in GPUs. And these hosts are connected by the DCN, which is the slowest bandwidth. And between host and the TPUs you have PCI, and between the TPUs you have this ICI connection. Sorry, my slides are wrong here, so it will be good to fix it here. So this direction is actually reversed. So you have higher bandwidth for ICI, then PCIe, and then DC. So here let's try to answer each of this question. So the best possible way would be so that we only stay in ICI, and with the host we first transfer our data into this TPUs, and then we just like all gather on TPU 0,0 head, so that we can do all the communication pattern in ICI. So you can see here you have a array size of 16 gigabytes, which we got from int 8 is 1 bit, 1 into 128 into 1024 into 128 into 1024. So it's like total 16 gigabytes. And we just learned that it's in all gather the time taken is V by W, and in generally in the spec sheet they just mention about the bandwidth to go from here to here, but as all our devices are bidirectional, so your bandwidth is basically doubled. So hence the for bidirectional this 4.5 into e to the power 10 is for the bandwidth that is for TPU V5 E architecture, and this is doubled with bidirectional, and you just like take this we have 16 gigabytes and we have this much bandwidth, and it will take this much time for all gather, which is the fastest way to gather. So technically this communication pattern is not all gather, it's a gather, because we will be only doing gathering in TPU 0,0, but yeah, like still the time taken is same. And and to load from HBM to the TPU units, you have this ratio, and the flops where we saw in matrix multiplication it is 2BDF, and this is the flops for the accelerator, and this is the time taken for T math. So this was all part of the previous lecture, so please do revisit it. But yeah, this I shifted this question to this lecture because I wanted to explain why all gather is a good communication pattern, because it doesn't depend on the number of shards, and it is limited by the bandwidth, and as have ICIs have higher bandwidth, so you can just like gather it really fast. Another communication pattern that we are going to use is called as all reduce. All reduce is basically a combination of two patterns. It is called as reduce scatter and all gather. So in reduce scatter, if we go back, we take data from all devices, we do an operation and send respective chunks to different nodes. So here also we are doing the same thing. We are taking the different data, we are doing operations, as I said here, add, maximum, minimum, multiply, because these are all commutative operations. So this would be across A, B, and 0, what's the max? A1, B1, C1, what's the max? A2, B2, C2, what's the max? And then you can take, so along the columns, any operation you can add like along the columns, or you can mm, take a max or min or multiply, and then you in a reduce scatter you just like, so this one would be f any operation of a0, b0, and c0, and this one would be a1, b1, c1, any operation on that, and um, then you have done reduce scatter, and then you just do an all gather. So all reduce can be broken down into these two communication patterns of reduce scatter and all gather. So as all gather and reduce scatter have the same time taken, all reduce is twice costly as reduce scatter, or twice as costly as all gather. So based on that, let's solve another pop quiz. So the question is, let A be an array with shape int 8, 128, 2048, and this is sharded along xy, and the mesh is 2, 8, z. So 2 into 8, 16, 32 devices in total. How much memory does A use per device? How much total memory does A use across all the devices? So, so to solve this question, we have 128,2048, and I is sharded across x and y. So you have 2 and 8. You have 16 devices across x, y. So it is sharded. 128 is sharded across 16 devices. So it is 8. So z equal to 2, it means that we have this xy matrix and it is repeated along or replicated along the z-axis. So it is same along the z-axis. So you have data here for, so this is our mesh, 2, 8, z equal to 2. And each one is 8, 2048, as only I dimension is sharded. So to get the total number of bytes is just like multiply by 32 devices. Yeah. So per device is 8, 8 into 2048, and it is int 8, so it is 1 byte, as 1 byte is equal to 8 bits. So you just like multiply 8 into 2048, and to get the total you just multiply by 32 because you have 32 devices. So another communication pattern in this chapter is called as all to all, and to better understand all to all, I have prepared a visualization. So this visualization will be on mixture of experts. It's a earlier in the transformer architecture from Vashwani, like the attention is all you need paper. The MLP layer was a up projection layer and the down projection layer, and the MLP layer is generally huge, and it stores a lot of activations, and it consumes the most amount of number of parameters in your transformer, and it has a lot of activations and consumes a lot of flops. So over the years, people have found that they can get around this. Instead of multiplying with a big matrix, they can get around by picking mixture of experts architecture. What happens in mixture of expert? So you have, let's say you have multiple many tokens in your sequence. In transformer, this would be individual tokens, and each of them is assigned. So actually, let me go back. So you have multiple tokens. So each of them, we have set top k routing. So we want each token to go to 2 experts. So you can see here T0 goes to E1, expert 1 and expert 2. And similarly T1 goes to expert E0 and it goes to expert E2. So this is generally picked up by a load balancer, or in modern methods there are no we try to make it balanced across the experts so that uh, all the experts are utilized. But generally these experts stay in different devices. So how, let's see how we are going to do mixture of experts. But before that, let's go through the mixture of experts example. So you have different tokens and you go to different experts, and in the next step what we'll do is each expert will gather its own tokens that it's going to process. So you can remember like T1 is in the expert E0 and also in E2 bucket. Similarly, T2 is here and here. So we selected two experts per token, so they are divided up like this. And now uh, now they do their matrix multiplication just with the expert that they have, and you have your outputs now after E0 MLP. So each of these experts are just smaller MLP layers. That's what it buys us. So instead of each token going through a big matrix multiplication, now they go through a smaller matrix multiplication. Uh, and after they go through the matrix multiplication, so then you have aggregation where you, so T0 went to expert 1 and expert 2, and it had probability of going to expert 1 as 0.55 and probability of going to expert 2 as 0.45. So then we just like weight the outputs from each of these expert by these probabilities, and then we take a sum. So now you have processed processed each of these tokens, and because of sparsity you are avoiding multiplying with a bigger matrix. So let's see how all to all works here. So I'll select here all to all, and I'll go back. Yeah, so we will pick top k routing to be 2, and we have each token here. T0 goes to expert E1, goes to expert E2, T3 goes to expert E1, E3, and it goes to E1 and E3. So each of these tokens go to at most 2 experts. And now in the next step, so as the experts are sharded across different devices, so each expert own their own device. So now you just like send over the tokens to each of those devices, and now all to all communication comes in. So if I go back here, so you can see here all to all communication is, suppose like this one, here you have multiple tokens, and all these tokens like this token is saying that I want to go to expert A, and here it is saying expert A it wants to go to the expert A. So you can see here, based on the indices, you are just gathering all those things, just the first one here, and all these things here, and CFI here. So the idea is, based on whatever expert the model picked, we are going to transfer them to their respective devices. So you can see here like we assigned different experts. Now we are going to do transfer with the all to all communication. So you can see device 0 receives the experts that were assigned it to it. So device 0 has expert E0, and it gets all the tokens that it wants to process. So this is the all to all communication. So all the experts which had indices of 0 or expert 0 go to this device. All the tokens, sorry, I'll walk back. All the tokens which had indices of expert 0 come to this device. All the tokens which are indices of expert 1 come to this device, and so on. And each token can be routed into multiple experts. So you can see here T0 is here, T0 is also here. So all-to-all communication is based on indices of the experts, and where the experts are present in the devices are assigned. Um, so all-to-all communication helps you with that. So you can go to next step, and yeah, you do the local matrix multiplication for each of the tokens assigned to expert 0. It does all the local matrix multiplication, and then another time we do an all-to-all communication, so that uh, all the devices now have all the experts have the tokens that they need to process. And after that, we have to do the step where, if I go back here and this weighted sum step, so this weighted sum step is done in that second all-to-all communication. So just go through this visualization and try to understand how mixture of experts play with this all-to-all communication. And after like doing all the communication, we just like dispatch them to different to all the devices, and this one will be processed later in the later transformer layers, or they will be used for decoding. So we went through all to all. So before doing this pop quiz, we'll be going through different cases of sharded matrix multiplication. Now we will be discussing about different cases of matrix multiplication and when they are sharded in this Streamlit application. These are the cases that are discussed in the book, and we'll be using this visualization. So case 1 is non-contracted dimension. It has no sharding. So it means, so you have a matrix I, J and JK. So you can say that this J is the contracting dimension, and this is not sharded. And if you see all of this example, like this contracting dimension, or where you multiply, you do the dot product between this column of this A and the column of B and the row of A, where you do the dot product, it is not sharded. And in all this example, if you see, J is not sharded at all. So the other dimension can be sharded. So here, if you can see, so A IX, so I dimension for this A matrix is sharded. So the local matrix multiplication has this I dimensions sharded, but in none of these cases the contracting dimension is sharded. So you can see here an example. We have 4 devices, and we have sharded I. So you can take it back, and so that there is no sharding, but for visualization purpose, let's keep it at 2. So you can see this block of A multiplies with this block of B, and this block of A multiplies with this block of B. Similarly, this block of A multiplies with this block, and this block of A multiplies with this block. And as the contracting dimension, which is along this column, along this dimension, is not sharded, so you can do this local matrix multiplications. So after you do this local matrix multiplication, all these partial results are present in all your devices, and yeah, then you can choose to replicate them across all your device. Then you have to do an all gather, but yeah, the main task was to understand if you have the contracting dimension, which is along this and this axis, not sharded, So you don't have to worry about it. You can just like do local matrix multiplication. Let's go to the second case where one of the contracting dimension is sharded. So you can see here I, J. So J is sharded along the X mesh axis. So if you remember our sharding visualization, so this is the X mesh dimension, this is the Y mesh dimension, and this is the logical data I and J. So you have J sharded along X, and so okay, let me unclick this. Yeah, J sharded along X. So you have to do this matrix multiplication of I comma K. So you can see here in case 2 there are actually two options to do it. So we'll go through both of those options one by one. So the first option is all gather, where what we do is for J, which is sharded, which axis is sharded, you gather this so that you can unshard this axis. Now you have Aij, so you can do just two matrix multiplication. So if we see it in visualization, let me go back just. So you have A here and JB is fully replicated, which is J comma K. So what you do is you all gather. That's it. You collect all the pieces in here. As you can see, you can call. So this device originally had only this one. Now it collected all of these things, all of these shards, and then you do your matrix multiplication, and you get the fully replicated result. Another option is alternative strategy is local matrix. So I'll go back here. So what it does is like, yeah, one of the dimension is sharded, JX is sharded. So what it does is it does a local matrix multiplication and then it does a all reduce. So let's see what's happening. So you have A, which is sharded along the X dimension, along the here we just have only one axis of devices, so it's sharded along this number of devices. So you can see A sharded, and the next step we do an outer product. So this outer product is basically every element, it's basically broadcast, and then you multiply across all the elements here and you get this outer product. And you can see every device as it has so B here, in if I go back one step, so B was completely replicated across all the devices. Now if you see here, only this chunk and this chunk is what is required to get the partial unreduced form matrix. Like with outer product you get just get the partial matrix. Similarly this one and this one you'll get a partial unreduced. Similarly for all of them. Now the next pattern is you have an all reduce, where you take, so if I go back, so it was partially unreduced, so you got this outer product but you had only partial slices. Now to make it a dense slice you use all reduce. In all reduce you basically collect all the matrices in a buffer, all the data across the devices, you do some operation. In this case it would be a addition, and then you do the reduce scatter operation, and then you do an all gather, so that you have all your devices are synced to the same data. So here you will be doing this all reduce operation, and as all reduce, as we discussed here, all reduce is twice as expensive as all gather, because all reduce is combination of reduce scatter and all gather. So we will be paying two times the cost here. And one thing to note is so these are like the partial unreduced, and when you do a reduce scatter, So each of the device gets its partial results, and then you need an all gather so that you can collect all the results from all these devices. So we discuss case 2 now. So case 2 has two strategy. One strategy is to gather on this axis and then do matrix multiplication. Here you pay once the cost, or you can do is like reduce scatter uh, and followed by all gather, and after doing the local matrix multiplication you can do this operation and you will also get the same matrix. So why would you pay extra 2 times cost? uh, so it can be uh, so we'll go through an example in the exercise where we will discuss about this communication pattern, but this can be helpful sometimes if so you can see here, uh, at the end of this all of these things are replicated. I comma k is replicated and we needed the all gather to do it. But if we don't need the all gather, then we can stop at reduce scatter. So if you stop at reduce scatter and you don't need to do the all gather operation, so uh, this operation would be of the same cost as all gather. And all gather also like you don't need replicated. And a good thing can be like here you are first doing an operation and then doing communication, and as uh, TPUs or accelerators are generally, they have a good curve with flops as compared to communication. So this operation might be good that you are first doing an operation and then doing communication, rather than in the earlier case you had to first do an communication of all gather and then do the operation. And here also if you don't need this replicated, then this is doing unnecessary device and then you have to discard the data. So all gather and the other alternate strategy are can be used based on the context that you are using it. The next communication pattern uh, is is where both the operands on are sharded on J. So you can see here J is sharded here and also it is sharded here. So this one, so you can see here like all the operations are sharded. So you can do this outer matrix multiplication again, and then you have to do this all reduce so that it is replicated. So the reason we are doing generally all reduce is we want all of the slices to have the same matrix after this multiplication. So um, there is an alternative strategy where you can do the following. So you have this and then you do the local um, outer product, you have partial and reduced, and then instead of doing an all reduce which has replicated, you can just do reduce scatter. And in reduce scatter it's like you don't pay the price of all gather, so this communication would be less as compared to the all reduce that I showed you earlier. And just the caveat here is you don't have replicated matrices. So if you want replicated matrices, then do not use this. You have to do all reduce. But if you don't want replicated matrices, then you are okay with using this reduce scatter operation. The case 4 is very simple actually. So you have like it's called as invalid, same axis, non-contracting. So all this non-contracting dimensions, this J and K. So J is your contracting, I and K are sharded. So you cannot do matrix multiplication on this. So you have to like gather one of them and then do matrix multiplication. Similarly, you can either also gather the B, which is K, you can gather it and then do matrix multiplication. So this case is simple. It's just like if you shard it on the non-contracting dimensions along the same axis, then you just need to do an all gather on either on the A non-contracting or B non-contracting. You can just do it and then just do the operations. So it will be very similar. You have a b, you just do the operations, you do all gather on a, you do all gather on a, and then you do the operation. That's it. So we covered all the 4 cases in matrix multiplication, and this UI will be in the comment section, and please feel free to play around the UI just to navigate the steps to understand what's happening, what communication patterns are happening. So we discussed about reduce scatter, we discussed about this question, we discussed about all to all, and now we will go to this pop quiz. So the question is, using the numbers from part 2, how long does it take to perform the all gather? So EY, and we need to gather along this EY axis EF on TPU V5E architecture of a 2D mesh 8,4 mesh axis, and it has given different dimensions. So let's go through this one by one. So you have EY and you want to gather along the Y dimension, get a EF, and you have this mesh axis 8,4. So your dimension is E, F 2048, 8192, and it is sharded along the Y mesh dimension. So you have along the Y you have 4 devices, so 2048 divided by 4, 512. So each one has 512, 8192 matrix, or 8.4 MB, and because it is like BF16, so yeah, it's BF16, so it's 2 bytes. So TPU V5E architecture has a bandwidth of 4.5 into e to the power 10, and if it is bidirectional, where this one can send data here and this direction, then it's basically you have double bandwidth. So in TPU V5E architecture, there is no wrap around where this device can directly send to this device. So this device cannot directly send to this device. So the worst case scenario is you have to do 3 hops where this data is transferred here, transfer here, then transfer here. So the worst case scenario that you are going to consider is 3 hops. That's like a worst case scenario analysis. So TPU V5 has no wraparound. Worst case scenario is 3 hops, and we discussed like each shard has 8.4 megabytes of data. So you have 8.4 megabytes, and the latency per hop, like 3 hops, we have 3 microseconds of latency. And okay, sorry, I got confused a little bit. So as we discussed in all gather, if I go back, so the total time taken is V by W. So V is the total shape of the array. It's not shape of the size of the total size of the array. It's not size of the array in one device, it's size of the array across all the devices. So if we consider that, then we have to multiply with 4, because earlier we divided by 4 because it was EY and it was sharded along 4, and we just like divided by 4. So we just need to get the entire size of the array and then divided by the total bandwidth, as it is bidirectional. So we have TPU V5 is 4.5 e to the 10, and it's bidirectional, so we just like multiply by 2. So we have this much millisecond, and there is like at least we have 3 hops, and each one has latency of 1 microsecond, and so total latency is 3 microsecond. So this is like very, very less for what we are paying for doing the communication in the TPU, and we can ignore this latency. Another example also, like if we didn't have bidirectional, then we had to divide by 4.5 in e to the power 10, and we had to pay the cost of 3 hops. We have to make 3 jumps every time, so it would increase our um, um, mm, time taken. So you can see here, if in bidirectional is around 377 microsecond, and it's now 560 microsecond. So it's gonna increase because we do not have access to bidirectional. We have to walk through the each hops, and which is the case in TPU-V5A because it doesn't have a wraparound. This device cannot communicate to this device. Another part of this question was where it reduced the size of E and F. So when we'll go through the same exercise, you can see is 32 kilobytes, and yeah, we'll consider it is not bidirectional. So 32 kilobytes divided by 4.5 e to the power 10, which is 0.7 microsecond. It is less than the latency to transfer data from here to here. So here we are latency bound. So for smaller arrays, so we are latency bound, and for larger arrays we are bound by uh, we it will be good to have the bidirectional, then we can reduce the time taken, but other than that we are bound by the time it takes to transfer the data, and the latency is not it's very small as compared to how much time it takes to just transfer the data. So this was the purpose of this exercise. And the next thing, the last thing in this chapter was reduce, scatter, and all gather are reverse operations in forward and backward. So I generated this with Claude, and this is very helpful in understanding why. So suppose you have data 2, you have 3 devices, 2, 5, and 3, and in all gather you just like collect all those data. So 253 collected here, 253 collected here, here. So now you get um, uh, now you would get a gradient for each of them now, and you have to send back the gradients to each of those devices. So, and to do that is like you have to um, do a backward pass of like reduce scatter. So you can see here 1, 2, and 0. So along this axis you sum the gradients, and along this axis you sum the gradients. Sorry, this is messing up. Along this axis you sum the gradients, so it's 3 plus 1, 4, and along this axis you sum the gradients, 4, 1, 2, 7. So all gather and reduce scatter are basically, if you're doing all gather in the forward pass, you need to do reduce scatter in the backward pass. Similarly, if you're doing reduce scatter in the forward pass, you have to do all gather in the backward pass. So let's go through all these questions fast, and yeah, I'll provide you my solutions for these questions. And also I didn't get time to finish up all the questions, so I finished up to question number 4. I'll be doing the rest of the questions and I'll be presenting in the next video. So so the question is, an array is sharded ix j k in the max axis 482. What is the ratio of total number of bytes taken by A across all chips to the size of one copy of the array? So you have mass of this, and you have sharded ix I along the x mass axis. So I is sharded along the mass axis. So it is saying what is the ratio of total number of bytes taken by A across all chips to the size of one copy of the array. So so one copy of the array is basically like the entire sharded one, and just yeah. So here one copy means that it's the total array. So you have array and you have sharded along the x-axis, so it's just the one copy. I also got confused by this question, but the one copy means that is I is sharded across the 4 devices, and yeah, like that. So the total shape is ijk. So if it has asked what is the shape in each device, then you can say I by 4 jk. So you can get the total shape here. And you can see here, like, it is sharded across x, but it is repeated along j and k. So hence you just like multiply them, so it's like ratio is 16. um, yeah, this question, yeah, this is the question that we were discussing uh, here. If we go back to sharded matpal, we go back to case 2 where we had two options to do this thing, where you just like all gather on the j axis and then you do matrix multiplication, and in another one you just do the local matrix multiplication or the outer product and then do an all reduce. So we have to see which one uh, is uh, what's the ratio of byte taking, sorry, yeah, like which one is better for this shape. And for this I will go back to my solutions here. Yeah, so let's read the question again. How long should all gather take on TPU v4 v4 p 4 into 4 into 4 slice with mesh this much, and b equal to 1024, d is equal to 4096 in bf16? How about all gather? How about all reduce? Right. Yeah, so first, so sorry, my bad. This question is not related to the case 2, that will come in further questions. So we have to do an all gather along the x-axis. So currently it is, we have a mesh of x444. So we have this dimension 1024 comma 4096. It is divided along the mesh axis 4 and 4, and you get these two, this matrix. So each one has a dimension of 256,1024 or 0.54 megabytes. So all gather means along the x physical axis, uh, along the x physical axis. If I go back here, you can see here it's x. Along the x we are going to collect the shards. So each one is 256,1024, and we are just going to collect all of them. And as we discussed, the time taken is v by wic, the bandwidth for ICI connection, as we are doing just TPU to TPU connection, that is ICI. It was discussed. My bad. Yeah, it was discussed here, TPU to TPU ICI connection, and you need to just do that. So v is the total size of the array, just like I have confused myself many times. V is the total size of the array, so it is 1024 4096 into, it is bf16, so it's 2, so divided by, as it is bidirectional, so you can do 9 8 10. So this is the time taken for all gather along this axis. Now it is asking if you have to do all gather along x and along y. So you can see here it's along x and along y. So this was, if I go back here, along x and along y. So you have this thing, and yeah, like so in all gather you are doing all gather along two axes, hence you have to multiply by 2. And also, so this one can receive data from, so all of these are bidirectional, so this one can receive from here and simultaneously also receive data from here, so hence the bandwidth also becomes twice. So this would take around 46 microsecond. So yeah, these are the just two modifications to be so in general in all gather, if you are all gathering along only one axis, then you just like do here. But if you're all gathering along two axes, you just like multiply by 2 and divide by 2. Okay, and then now it is asking about all reduce, and we discussed about all reduce. All reduce is 2 times of all gather, because it reduce scatter plus all gather, and both of them have the same communication pattern, so it's just you have to pay the price twice. And another thing that was very important in this question was, you can see here like the z axis is not sharded. Even if you have a mess of z4, it's not sharded. You just have you're just like repeating your data across along the z axis, which is not very helpful. Like, so you just like take this cube of data that we found, uh, and it came from here bxdy, so you're just like dividing each of them. And so it is like 256,1024 is repeated along this entire uh, dimension, which is not good. So what you can do is you can shard 256,1024 along the z dimension too. So um, so that way uh, yeah, replication along the array along the z-axis is not ideal. um, and to to solve that problem, you can replicate along the z-axis. And one thing that we discussed here was, sorry, yeah, the x here cancels out, so it doesn't depend on the number of shards you have. It just like depends on v and what's the bandwidth. So even if you shard along the z axis, you are not going to pay a lot of price because it doesn't depend. And now you can have more bandwidth to play with because you have another axis where you can just like gather the data from in simultaneously. And this operation was to all reduce. Okay, this was the it was like twice as expensive as altogether. That's what I wrote. Yeah. So now let's go back to our exercises that we're solving. Yeah, here let's say we're performing all gather bx. B is very small, say 128. How long this should TPU for slice with max size to take this? So we have along this axis, so we have 4, 32, each one is 32, and the time taken, so number of hops is 2. There is a wraparound. Actually TPU v4p has a wraparound. TPU v5e didn't have a wraparound. So you can get it by x by 2, and the number of hops is 2 millisecond, and the time taken is v by wici. And yeah, this is very very negligible. So it's like bf16, and this is like dimension of 128. So this is very very negligible, almost equal to 0. So you are bottlenecked by the latency. So the main theme is, if you have smaller arrays, then you are bottlenecked by the latency, and it is irreducible. You cannot reduce this latency. But if you have like larger arrays, then you are amortizing the cost for the latency. Yes, now this question is kind of important. I would definitely suggest you to go through this slowly. So to perform matrix multiplication BD, and you can see here D is sharded along X. So it would be like, so it would be same as case 2. Here is one of the dimension is sharded, so either you can all gather along the dimension and then do matrix multiplication, or do matrix multiplication, local matrix multiplication, or the local outer product, and then do all reduce. So this one would be, instead you could multiply the local shards. So this would be the all reduce case, and this is the all gather. So we will compare the flops and which is better and why. So first we'll cover, okay, you have BD and DF. So this part you can all gather. So you just like all gather this part of the matrix, and then yeah, like in all gather you are just as I said, you are just like paying for the total size of this array, which is 2, comes from bf16. Df is the size of this array by wci, so it's like v by wci. So Yeah, I cross-checked in their answer, but like this one here, um, apparently like this part, like where to read, to do the actual matrix multiplication, which is like read and this is write, which we discussed in video 2. They didn't consider it. I have asked this question in the comment section. Let's see if I get a response. um, so flops is to BDF. We discussed this extensively in lecture 2, and the time taken for math is to BDF into accelerator flops. So you can, so if you want to be um, math bound or flops bound, so this ratio should be bigger than this count. But yeah, like if you are communication bound, if your batch size, not batch size, this B is less than C comma W ICI. So yeah, like you, here you have a so you have control over the B. You can tweak the B based on the accelerator flop and the bandwidth to change to uh, to go into compute bound region. So if you increase the B beyond this, then you will become then you will be math bound. Now you are, if your B is less than this ratio, then you are compute bound. The other strategy is where you take this and do this matrix multiplication, and then you do the the reduce scatter operation, and then you do the all gather, what we discussed here. Yeah, this one. So we did this operation, we did the outer product, and each one did a reduce scatter on whatever slices that they want, and then we did an all gather. Yeah, you can do this operation. So to BDF, so you can see here, you're in a matrix multiplication, this D dimension is sharded, so your total math is also divided by the shard size XC. So you have this much, and um, so, and this communication is twice the communication for reduce scatter. So it's like you have to be, so you do this, you take this BF, you have to do reduce scatter on this, and then you have to do all gather on this. So you are paying a lot of cost. So it's 2 BF, this BF16, and this is 2 times because it is all reduced. So you have this much cost. And to be comms bound, you have to have this D by 2x. Yeah, so you are communication bound if D by 2x is greater than C comma WCI, or you will be so you don't have any control over B here. You have control over the second dimension, which is D. um, Second the contracting dimension, which is generally the weight matrices dimension. So B would be like something like the batch size, which you have control over. You can increase the batch size, you can feed in more data, and go into with this approach you can go into compute bound region, but here you cannot go into compute bound region. So this is the comparison of all gather and all reduce, and it kind of depends on what things you want to control, what things you have control over. If you can increase your B, go into compute bound region, that's great, but otherwise you have to control the D, and also the number of shards. It depends on the number of shards, all reduce. That is it for this lecture, and we'll be solving over the next question in the next lecture.